All right, let's jump right into this explainer and demystify one of those classic and honestly kind of tricky circular route coding challenges. If you've spent any time prepping for technical interviews, you know exactly what I'm talking about. The infamous gas station problem. On the surface, it looks pretty straightforward, but it's got this hidden depth that turns it from a run-of-the-mill coding exercise into a genuinely fascinating puzzle of logic and optimization.
So what's the immediate, brute force reaction most of us have? We just want to write a nested loop. Start at station 0, simulate the entire trip. If that crashes and burns, start at station 1, simulate the whole trip again. And just keep doing that. But rather than brute forcing our way through every possible scenario and totally draining our processing power, we're going to solve this mystery by finding a really elegant shortcut. We're looking for a highly optimized approach that feels a lot less like grinding out code and a lot more like cracking a safe.
Okay, the main goal for this road trip is straightforward enough on paper. We just need to determine the exact index of the gas station we absolutely must start at to make one complete, full loop around the circuit without the car running out of gas. And, hey, if it's impossible, we just return -1.
But before we put the key in the ignition, we have to establish the ground rules. First up, your car always begins with a completely empty tank. Zero fuel. At every single station, you gain a specific amount of gas, and driving to the very next station consumes a specific amount of gas. Because we're starting on empty, we have to calculate our fuel consumption step by step to see if we can literally go the distance. Oh, and the problem actually gives us a really nice lifeline. If a solution does exist, there is only one uniquely valid starting station.
Now, the very first logical check we need to run before we even think about driving is a high-level sanity check. We need to compare our total available gas across all the stations against our total travel cost for the entire loop. Why? Because if we don't have enough total gas to cover the overall trick, meaning the sum of our gas array is strictly less than the sum of our cost array, well, it's an immediate dead end. No matter where you start, physics just won't let you finish. But if the total gas is greater than or equal to the total cost, a solution is absolutely mathematically guaranteed to exist somewhere in that circle. Picture what we're starting with here. We've got two distinct arrays staring back at us. One array represents the gas we gain at each specific station, and the corresponding array directly below it represents the exact cost to move from that station to the next one. But honestly, trying to look at them separately makes it really hard to see the matrix, so to speak. So instead of juggling gas and cost as separate, disconnected numbers in our heads or in our code, we can just subtract the cost from the gas to find the net gas at every single stop. And let me tell you, this is a real game changer for our logic. It immediately gives us our real fuel profit or deficit at a single glance. Positive numbers, that means we added extra gas to our tank for the next leg of the journey. Negative numbers, that leg drained way more than we picked up. All right, let's test drive this and start tracking our tank with a simulation from station 0. At station 0, we gain a net gas of 1. Awesome, we have enough to move. We slide over to station 1, where we gain another net gas of 1, bringing our total running tank to a comfortable 2. So far, so good, right? The road trip is going smoothly. But then, suddenly, at station 2, we hit a massive speed bump. The net gas here is a harsh deficit of -3. We only had 2 in the tank, so dropping by 3 puts our tank at exactly -1. This means we literally ran out of gas trying to reach the next stop. We completely failed the simulation starting from station 0. Okay, so we clearly can't start at station 0. Now, if you're writing a brute force algorithm, what's your natural instinct? It's to just back up, increment the starting index by 1, and try the whole agonizing process all over again starting at station 1. But hold your horsepower, because doing that is exactly what makes the brute force method so incredibly slow.
Instead, we need to apply this golden rule. If our tank fails at a specific station, let's call it station B, after starting way back at station A, then starting anywhere along that exact same failed path won't magically give us enough gas to pass station B. It's logically impossible. And if you visualize our gas tank over time, it brilliantly illustrates exactly why this is true. Our tank maintained a non-negative, healthy amount of fuel all the way from point A right up until the crash at point B. Those earlier stations were actually subsidizing our trip. They were providing positive net gas that built up a crucial buffer. So starting later in that specific sequence just means we'd be missing out on the positive fuel buffer we desperately needed from those earlier stations. Think about it. If we couldn't make it with a head start, we definitely can't make it by starting closer to the deficit.
Let's move forward and see how this builds our highly efficient shortcut. Since we failed at station 2, we can entirely skip testing stations 1 and 2 as starting points. Just throw them out. We jump our next valid attempt all the way to station 3. We reset our tank to 0 and start driving. But as we trace the math forward from station 3, we hit a -4 net gas at station 5. The tank drops below 0 again. We hit another dead end.
No worries, we just apply our golden rule again. We skip past that entire second failed segment. We don't even bother checking stations 4 or 5. We restart our road trip directly at station 6. And hey, look at that. From station 6, our tank stays positive. We successfully make it all the way to the end of the array at station 7 with gas to spare.
But right here is the big mystery, and honestly, it's the part that usually trips people up. Do we actually need to write code to simulate looping all the way back around to the beginning of the array to definitively prove station 6 works as a full circular route? I mean, we've only reached the end of the list, not the end of the actual circle.
Amazingly, no, we don't need to simulate the loop at all. We can figure this out with a quick proof by contradiction. Imagine if no valid starting solution existed anywhere. That would mean the entire circular route is just made up of continuously failing segments. Every time you start, you eventually hit a deficit. Now think about the math behind that. If every single segment ends in a deficit, it means every segment has less gas than cost. And if you add all those segments together, it would mean the total sum of gas for the entire circle is strictly less than the total sum of the cost.
But wait, remember our very first logical check from the beginning? We already verified that our total gas is greater than or equal to our total cost. Because we know a solution absolutely must exist, and because station 6 is the very first point we found that doesn't fail before reaching the end of the list, the math guarantees it has to be our unique starting point. The excess gas we accumulated from station 6 onward is mathematically guaranteed to be enough to carry us through the deficits of those earlier failed segments when we loop back around. It's brilliant.
This is exactly what makes this greedy shortcut so incredibly elegant and efficient. By just making the optimal local choice, meaning skipping ahead whenever we hit a deficit, we find the global starting station in just a single O of n pass through the array. We don't use any extra arrays or memory, keeping our space complexity to a perfectly constant O of 1.
Now, a quick piece of insider advice for you. If you ever find yourself sweating during an interview because formally proving this greedy solution by contradiction on a whiteboard is just way too intimidating under pressure, and let's be real, it is, a highly pragmatic tip is to openly acknowledge that to your interviewer. Just tell them, hey, a form of mathematical proof is tricky here, but let me show you the logic. Then simply trace your algorithm through a few diverse examples. Visually proving that skipping the failed segments works will confidently demonstrate your engineering logic, even without a formal math theorem.
The absolute beauty of this problem is how it tricks you into thinking you need this massive, heavy simulation when all you really need is a little bit of logical deduction. I hope this explainer has shifted your perspective on algorithm design a bit, and maybe leaves you wondering, where else in your daily coding can you skip the heavy brute force simulations and let a sleek, greedy algorithm do all the heavy lifting? Keep looking for those logical shortcuts, and happy coding.